Up to molar mass, and that's where we're going to stop today before the break. And then when we get back, we probably won't have time to do the lab today, but when we get back, we will for sure do the Benium lab. Okay, so the concept of the mole. Up until now, we've talked about ratio of atoms and ratio of masses. We were able to take the masses off the periodic table and apply the unit AMU to them, okay, just like the homework. But I wanted to point out a few things. Up until now, we've talked about, for example, one carbon atom, right? And we've said that one carbon atom has an atomic mass of 12.01 AMUs. Where did we get that 12.01? From the periodic table, right? Perfect. Okay, now this is one tiny, tiny atom. Can we see one carbon atom? No, but can we see maybe a large sample of carbon atoms? Yes. And so now we're going to start to introduce the mole. We've still got to use the ratio of masses, but we've got to take out of thinking of AMUs. We're going to start looking at grams now. Okay, but grams is not as small as atomic mass unit. It represents a much larger size. So, okay, up until now we've looked at ratio of masses. And we know that if the ratio of the individual masses is the same as the ratio of my sample mass, then we have identical number of particles. Okay? Identical number of particles. Now, does everybody understand what that truly means, or do you need clarification on that?
Clarification, please.
Okay, thank you for asking. So, let's assume that we have one atom of two different types of atoms. So, let's say one carbon atom and we'll use the example here, one nitrogen atom. Okay, according to this, and according to our periodic table, how much is one carbon atom, how much does one nitrogen atom weigh in AMUs? 12.01 AMUs and 1401 AMUs, right? Okay, so when we talk about the ratio of individual masses, all we have to do is compare two samples to each other, correct? That's what a ratio is. So I can draw a little division bar in between that. Does it matter if the 12 is on top or the 14 is on top? No, all I'm trying to do is set a ratio. So what is, someone will pull out their calculator, what is that ratio of carbon to nitrogen?
0.857.
0.857 is enough.
Yeah.
Okay, so that's the ratio. Now that's for one carbon atom and one nitrogen atom, right? Okay, let me have two of each of those atoms. So two carbon atoms and two nitrogen atoms should weigh what? Well, 12.01 times 2 is 2402. Okay, 1401 times 2 is 2802. What is this ratio?
The same.
It's the same. Okay, that makes sense. Do you think that would be the same if I had 3 carbon atoms and 3 nitrogen atoms?
Yes.
Okay, so what this says right here, that as long as the ratio of my sample, okay, equals the ratio of the individual masses, I have identical number of atoms. I have 2 carbon atoms, 2 nitrogen atoms. That's what it means by the identical numbers. So could I do this on a much larger scale, like 500 of each of those?
Yeah.
Yes, as long as this ratio is the same as this ratio, I have identical number of atoms. So when we talk about the mole is used for all elements on the periodic table. Okay, and it says, for example, a sample of carbon weighing 12.01 grams, not AMUs now, has exactly the same number of atoms as a sample of nitrogen that weighs 1401 grams. Why can we assume that 12.01 grams and 1401 grams, so this is carbon, this is nitrogen, has the same number of particles as each other. Because this is the exact same ratio, whether it's in grams or AMUs. Still applies to this concept right here. Okay? And so you should be able to calculate the mass of any element that has the same number of atoms as long as you know the ratio of the atomic masses. So let's do this example real quick. What mass of copper has the same number of atoms as 40.47 grams of aluminum? Okay? So I'm comparing copper to aluminum. This 40.47 is what's given. Okay? I need to know the ratio of the masses of the individual elements. Where do I find those at? Periodic table. So let's organize our thoughts real quick. We have, what does 1 copper weigh?
12.1.
No copper.
No copper.
Yeah.
63.54.
5. Remember, we keep 2 decimal places and we round. So 1 copper is 63.55. What is 1 aluminum?
25 or 26.98.
98. Now, since we're dealing with grams, we can apply grams on the end of this. Okay? If we were dealing with AMUs, we could apply AMUs to this. So if this is the ratio of copper to aluminum, this is the individual masses, I can set this equal to my numbers here. So if I'm trying to solve for X grams of copper and I have 40.47 grams of aluminum, can I not set this up just as a proportionate? These have identical number of atoms because it's going to be equal to the ratio. Now we just have to solve this, just like we did in Algebra 1. Okay? So everybody know how to do a proportionate. Cross multiply if you need to. So cross multiply, X is going to be equal to 63.55 times 40.47 divided by 26.98. So what I would recommend is type all of this directly into the calculator, and then your answer should be reported to 2 decimal places here, or 4 significant figures is fine. And what do you get there? What do you get?
Oh wait, no mind.
95.33.
33?
Yes.
Okay, and so this would be grams of Cu. This is how much copper I would need to have identical numbers of atoms as aluminum. Now, there are several questions like this on the homework. What I would recommend is in your notes right now, because you're probably going to have to look back at your notes to remember how to do this, I would make a note to where you got these numbers, because when you go back and look at a problem and you're looking like, where did all these numbers come from? Make a note to yourself now that this is from the periodic table. Okay, and you can just set it up as a simple ratio. This one is copper, this one is aluminum. Okay? Questions about that? You know how to pop it in? Okay. All right, go to the next page. Okay, so this concept of ratios of masses leads us directly into how the mole unit was discovered, or how it is what to believe. So if we weigh out samples of all elements such that each sample has a mass equal to that element's average atomic mass, okay, this right here is what's from the periodic table. Okay, when they talk about average atomic mass, that's the masses on the periodic table. These samples all contain the same number of atoms. Okay, so you can pick any sets of elements up there, and as long as those ratios are the same as the individual masses, they have equal numbers. Okay, this number is called the mole. Now, it's abbreviated MOL. I don't know why they just dropped one letter, but it is. And the mole is defined as the number equal to the number of carbon atoms in 12.01 grams of carbon. Pretty much what we just did here. Everything has been compared back to carbon. Okay, now, scientists have precisely counted the number of atoms in that ratio to be 6.02 times 10 to the 23. This is called Avogadro's number. This is how many particles are in 1 mole of substance. Okay, you do have to memorize this, unfortunately, but you will use it so often that you will know it by heart. And Alex, you asked a question about having that extra 2. This is the number that we will use. So you will have the 6.022. Okay, so let's think about what 1 mole actually means. And I'm going to write out so you can see how long that number really is. Okay, sometimes it's hard for us to imagine that number. Okay, so 6.02 times 10 to the 23. That's how big the number really is. So when we talk about one atom is super small, right? But if I had a mole of atoms, if I had this many atoms, do you think that we'd be able to probably see that sample?
Yes.
I think so, because that's a big, big number, okay? And so this is how many particles, and particles can be referred to as atoms if we're talking about single elements. It can be referred to as molecules if we're talking about a molecule or a compound. But this is how many particles are in 1 mole of substance, okay? And so here, a mole of pencils. How many pencils would I have if I had 1 mole of pencils?
That many.
That many. Now, we don't like to write that many zeros, so we write 6.022 times 10 to the 23. Okay, if I had a mole of iPhones, a whole lot of money there. Okay. 6.022 times 10 to the 23 iPhones. Okay, let's bring it back to chemistry. If I had 1 mole of water, I would have 6.022 times 10 to the 23 water molecules. Okay? Does that make sense to everybody? Okay, it's a big, big number. Now, how are we going to use it in this class? Well, Avogadro's number is defined as a sample of any element that weighs a number of grams equal to the average atomic mass. Now, where do we find the average atomic mass?
Periodic table.
Periodic table. So, Avogadro's number, which is 6.022 times 10 to the 23, is defined as being equal to an element's average atomic mass, which Avogadro's number is also equal to the mole. So we can say also that 1 mole equals the mass in grams. So all of these are equal to each other. You're going to be using these as conversion factors in dimensional analysis. Okay, so 1 mole of aluminum. 1 mole of aluminum contains that many atoms and has a mass of 26.98. This right here was from the periodic table. Okay. 1 mole of copper contains this many atoms and has a mass of 63.55. Okay. Now, this is the main set of conversion factors that you're going to need to know by heart. You'll use them so often that you will commit them to memory. I do not give these to you, but I want to point out that yes, since both of these are equal to a mole, these two are technically equal to each other. But in this class, all of your work has to be shown that you're going back to the mole. So don't ever set average atomic mass equal to Avogadro's number. In your work, you have to set it equal to the mole, if that makes sense. Okay? So, let's look at the types of conversions that we're going to look at in this section. You'll pick it up fine because you guys know how to do dimensional analysis. Now we just need to look at where these numbers come from. Okay, so this first example, it says calculate the number of moles of atoms and the number of atoms in this many gram sample of calcium. So this is 2 sets of problems. Okay, each one is done separate from each other. We're going to always start out with what's given in the problem. So 25 grams calcium. It is very important that you label here because you need to know what mass we're having to pull. The first task is we're going to go from grams to moles. Okay, grams to moles. So if grams is here, I need to put grams on the bottom. Is there a connection between grams and moles? Yes. Okay. And so 1 mole of calcium is how many grams?
40.07.
40.08. Yeah, make sure you round to 2 decimal places. But now that grams cancel, I'm in the unit that I want. All I do is divide. Okay. So 25 divided by 40.08. Think about significant figures. How many sig figs will my answer have?
3.
3. Okay, so somebody type that in and tell me what it is.
0.623.
0.623, and then my unit is moles of calcium. So that's the first part. I'm going to label this 1. Okay. The second part, we're going to go to number of atoms. Now, typically in your homework, you won't have to do both sets with one problem. There'll be an entire section that all looks the same. So this would be an example of if I need to go between grams and atoms. Okay, I have to go to moles first. So I'm going to start out with what's given. So 25 grams of calcium. I've got to go to moles first. So 1 mole of calcium is 40.08 grams. Now that I'm in moles, can I go to atoms? Yes, so 1 mole of calcium is 6.022 times 10 to the 23 atoms of calcium. Okay, when you type this in, I would recommend, to make the least amount of errors, type in everything on the top. You can ignore the ones, and then divide by the bottom. Okay, so 25 times 6.022. Don't forget to use your EE button. Okay, don't use the times 10. Use EE. 23 divided by 40.08. Yes, sir.
On that,
Mm-hmm.
wouldn't we be able to take out the middle part and just go from the grams into
So from there, so on that page before, and that's why I had to put this as a disclaimer up here. I go, since both of these are equal to each other, technically you could, but for purposes in this class, I need you to go to the moles. Where it's going to carry over is when we get to stoichiometry.
Oh, okay.
You have to be able to go to moles. So theoretically, yes, it would work out in the same, but you will get credit for going to the moles. If you skip this step here, you will get counted off the point. Okay. Now, what is this when you type this in?
3.76 times 10 to the 23rd.
3.76 times 10 to the 23rd. Does everybody agree? Okay. Now, this is obviously one way. There was one other way that you could have done this. In the previous problem, we had already found moles. Okay. So if you had already found moles of calcium, could we not have just gone on and said 0.623 moles of calcium is 6.022 times 10 to the 23 atoms? You could have. Okay, so this process here and this entire process would have both given you this final answer here. Okay? So whatever you're comfortable with, or if you're already given moles, you can go straight from moles to atoms in other problems too. Okay? Okay, you go ahead and do the second one, okay, and then I'll call 2 people up to do them up at the board. And then we'll move on to the next page.